Good evening, everybody. So today is October 12th. So as you see that we are in the second half of this course. So now and one word. So you will see that our topics are not that much complicated, easy. If there is something complicated but interesting, I think even you will be able to understand this by your own pace. I will provide my lecture slides and then videos, and also there are a lot of online resources, okay, so that will be helpful. But these are the topics that are new, almost new for this course. And okay, that does not mean that I'm asking you to not to come in the class. Okay, please come in the class and join in our online in-class activities. There are 5% points for that, right? Okay, and then the reminder, there is some announcement. I found one questions, there's a mistake in quiz 3. I give point to everybody for that one. So that was the question about which of these are height balance tree. Both AVL tree and red blood trees are height balance. There was a mistake in my test question. Okay, and another announcement, there is a test. The test 2 will be next week, next Thursday. Okay, during class time, but this time, okay, test 2, during your test 2, please bring your computer and laptop. So because we may have one part of the test as MCQ, multiple choice questions. So if I give one part multiple choice question, you will take that part on computer, and then if I have another part in handwritten, then you will take that part. Okay, so please make your computer ready. Otherwise, maybe if you don't have computer, you can use here this laptop, but I cannot give a guarantee that this will work for you. So please bring your own laptop. Okay, and let me see, then I need to defer quiz 4 and assignment 4. I will think if needed, then I will move it to next week or a few days in middle of next week. Okay, but I like to keep them before the test so that you have practice. Before the test, I will keep the due date for quiz 4 and assignment 4. Hopefully I will upload tomorrow. Okay? And then please make your plan to start assignment 4 tomorrow or day after tomorrow, Thursday. It will not be that much hard, like our chapters like these will not be hard like as much as red black trees. Our complicated part and boring part has gone. Okay, so today we will discuss hash tables and hash functions. This is chapter 11 in previous weeks. So then I'm following the schedule from other professor. They put this way. Actually, I found there, I thinking that for these data structure and red blood tree, these are similar. So they put this together, and then this is something new concept. So as hash table and hash function, so it is, maybe many of you are familiar with this. Some languages like Java and modern languages has hash functions built in. Hashing is used to, like in general, like in English, what is meant by hash? To chop, right? To make slice. Okay, so I will upload a lecture video maybe tonight or tomorrow, but let me go with the existing one. the slide has two lectures, ABL tree and hash tables together. So we covered ABL trees, but some hash table is here. Okay. So we are familiar with dictionary, right? The paper-based dictionary. So in an old and existing paper book dictionary, we search a word. We search something for a word, right? For instance, what is the meaning of hash? How do we search it? So we search the word hash, okay, by its key value. Key is hash. The word itself is key. Okay, and then we search from the. If we start from the beginning, we pass A, B, C, D, E, F, G, H. When we first get H, then we start searching for hash, any word, right? So it starts with a key, and then whenever we find a word, and then on the right side we find the definition of the word, some examples, or some sentences, some uses, or alternative meanings, and a lot of some information. So this is the concept of like key value pairs. There is a key, like hash is itself is a key, and the meaning of this word, whatever word I'm searching for, that's key, and that is values. So key value pair is another kind of data structure. For many purposes is used. If you are familiar, if you hear the name JSON data file or something like or dictionary, some languages are dictionary also, key value pairs. Okay, so think about that. Our traditional data structure like array. Okay, how an array element is accessed and stored. An array element is searched and accessed by its index number, right? So for every index there is a location. For linked list, stack, and QE, we search element, stack, QE, and table and trees, ABL trees, binary trees, and red-black trees. We search an element by its location. Okay, so the hash table is the concept is that we will search element not by its location, by its key value, key. Okay, for instance, we have dictionary. We are giving an example of traditional dictionary. Like, for instance, a dictionary has, think about it, 50,000 word. The dictionary has 50,000 word, right? If we index the dictionary, each word has index maybe 0, 1, 2, 3, 4, 5, 6, 7, something like this. And if we are searching a word, maybe the hash, the word hash itself, and maybe its position is 15,021. We do not search by 15,021 that location, right? We search it by where is the word hash is located on which page, right? So this is the searching is called, we search by its key value. Key is hash. So okay, so there's a misleading word over here, key and value. Don't concept mislead as key value pair. In that case there will be hyphen, key hyphen value pair, not key for a key. Okay, but what I'm going to tell you that we search a word in a dictionary by the word itself, not by its location. You understand? Which position is not, we don't search. Where it is, we search for this. So our concept is the hash table is something like to build a table for which we will be able to search the word or search the item by its value. So then how we will search it by its value? Sometimes we can search it by real value, or sometimes it's modified value. So how do we modify the values? We modify the value based by some hash functions. Okay, another way sometime. Okay. So we will see how do we hash or some split or rearrange some data in a hash table based on this value. Okay. So one thing is, remember that unlike traditional data structure, array, linked list, tag, queue, trees, hash table is different, right? What is the different? What is the different? This is the we access an entry or an item by its key value, by its key, not by its location. Okay, because location can be changed based on the hash function. In my hash table, location of, if I have a data set, and if I am given an option to use any hash table, so my table may be different and your table may be different, both will be correct. Okay. So since we will be searching an item in a hash table by its key, so that in an average case the running complexity, time complexity is constant, big O n, big O1. Okay, but we know that in a linked list running complexity sometime in the worst case big O n, right, theta n, but here it should be constant, and sometime it is pretty constant. We will see that why I say sometime. In some rare cases we will not be, but pretty constant. Okay. So here, so for instance, I have a value key, I have a key 33. Okay, I have some values like 33, 30, 43, 31, 25, some numeric numbers. Okay, and then I want to make a hash table. So this table is, look at this, since this table looks as a traditional array, right? But it is an array, but it is kind of special array, because in a traditional array we need a array size, sometimes maybe large size, word, or small size. Okay, so here our value, our key is 33. We want to put this in a table. Where we should put? Okay, that depends on it. Where I will put, that depends on my hash function. Okay, so what is hash function? Hash function is a function that uses this key, okay, and generate another value that will be related to this value, and usually we use that value to put this value, newly generated value, to put this value in a table. For instance, if my hash function is modulus function, it takes modulo 10. Whatever number I put, 33 I put, it takes the remainder when I divide it by 10. So then when we divide by a number, divide by 10, that is 33, we divide by 10, the remainder will be 3, right? So 3, we are getting that we can consider that this is the index of my table, hash table. Okay, so and that position with index 3, I will put that value 33. So the value itself is telling where this will be located, right? And then similarly, if I have another value 45, and if I use same hash function, then that will take index. Okay, so 45. Okay, let me take 42. Maybe 42. Then index will be 2. Okay. And here that will take this position. 42 will be taking this position. Okay. And now the question is that which function I will consider for hash functions. So This is why our goal is to select a good hash function. So the goal of a good hash function is to distribute these keys nicely in a table. Okay, hopefully each value will take each other's place. There will be no overlapping, but sometimes there will be overlapping, and there are some ways to resolve those overlaps. Okay, so we will see this. Okay, and one of the application of hash tables and hash function is that for security purpose, like privacy or security. If you had that, for instance, sometime we encrypt our data for password encryption, and for other purposes we need to encrypt our data. Okay, so whenever for those purposes, hash tables and hash functions, hashing is widely used. There are many hash functions, some ways, some are built in, some are well popular, and still there are a lot of research going on this area. Okay, we will see some example. Okay, so these are not that much difficult, so if you give attention one time, then you will understand. So our goal is a hash function over here. We will insert the actual key values, maybe 33, 45, 26, 100. Okay, and then what this, based on these keys, our hash function will create index. For instance, we are trying to put this data in a tabular format, in an array format. So in an array we need index, right? Okay, instead of a predefined array, okay, we will create our array based on these index values. How we will get index values? We will use the keys as parameter or argument to our function, and when we pass these values, then we will get these indexes will be generated, and then we will create a hash table. This is the concept. So our goal is to find a good hash function. What is the good hash function? A good hash function has the characteristics that it should be relatively simple and efficient to complete. It does not need to be too much complicated. Like for instance, just we saw that a hash function, okay, a hash function can take any modulus operation, sometimes maybe modulus 10, modulus by 5, modulus by 100, whatever is appropriate. Okay, and we will actually understand which hash function is appropriate based on our given data. Okay, so for instance, look at this. These are our key values. These are keys. Keys are given with string, right? String, so they are put in double quote. The string values. So we know that whenever we get a string value, then actually we need, in general, we need to generate corresponding integer numbers, positive integer numbers, okay, from the given strings. So there are many ways to generate corresponding integer numbers. One thing is that we know the ASCII value, right? For every character has ASCII value. So for ASCII value, T has ASCII value, ASCII code in the ASCII code. So if we search for ASCII code, ASCII table, okay, so for ASCII table, each character has its code. So here, for instance, T, we see that has ASCII value 84. T has ASCII value 84. O, lowercase o, has ASCII value 111, and M, lowercase m, has ASCII value 109. So 84, 111 and 109, these are the three values. Let us remember that. So here, as I said, you can use any method. So for instance, if we say that I will add up the ASCII numbers, maybe 84 plus 111 plus 109, whatever value I get, that will be my hash code. And one thing is that we will use same fashion, same math approach for all keys, unified. It is not that I will apply one process for this one, I will apply another process for this one. No, that will not work. We will use same thing. Okay, and for instance, as we know that every character has its ASCII value, so maybe we can use 84 plus 111 or plus 109, and whatever value we get, that could be your ASCII hash code. Or we can do something different. For instance, here in this example, since there are 27 characters in English, so for each character they put number. There are three characters. Okay, so for this, so then they put the each. So it's got quadratic equation, something like this. They put a polynomial equation over here. So 84 is t is ASCII value. 84 times 27 to the power 2. That means this position is 0, 1, and 2. So 27 to the power 2 plus 111 is O's ASCII value, lowercase O's ASCII value is 111, and then times 27 times power 1, and so on something. For instance, here, so they use this way. For instance, initially they are getting a large hash code for each of these string key values. Okay, and then now it will be goal to get a concise index, right? Index value from this hash code. So this hash code is really large number. It will be difficult to remember. This is how our goal will be, to make it concise or easy using a hash function. There are many ways we can do. For instance, here one thing is that we know that there are 5 characters. There are five keys, 1, 2, 3, 4, 5, right? So an easiest way, could be using modulus 10. So if you say module 10, then the right digit will be here, the remainder will be 2, here 9, then here 8, here 5, and then here 8, right? Okay, in that case, if we say modulus 10, then we need to have a table that has 10 different spaces with size 10. But we know that we have only 5 keys to hash. So why we are going to use double memory space? Let us, if we take modulus 5, then we will have some values between 5, right? So for instance, the remainder value will be not greater than 4, 0 to 5, 0 to 4. Okay, 5, if last digit is 5, then it will be 0. Remainder is 0, right? So here, taking modulus with 5, we got these values. Okay, now if we make a table with this 0 to 4 indices, and then we see the term has index, modified index value 2, that with index position 2, we are putting this key term. So that means this index is generated from this, right? And this is also generated by this itself, right, term. That means this index 2 is generated by term itself. So then that means there is a relation between this term and this number 2, right? They are not unrelated. Okay, and similarly, for instance, for Dick, we got index 4, so dick will go over here, right? Dick will go over here, dick will go over here. Okay, and similarly for Harry, so you can check. I did not check, this is another professor's slides, but I believe these are correct. Okay, so whatever it is correct or not correct, you will get the indices hash table between 0 and 4, not greater than 4. Okay, so it has 3, so then Harry will get in this position 3. So Harry will get this position 3, and the next Sam will get this position 3, 0, and the next Pete wants to take position at index 2, but there is a collision over here, because at this point, okay, it will know that the hash table will know that, hey, this position is already occupied by Tom, so you cannot sit here. If you want to sit over here, then Tom will be gone, right? In memory space we cannot put two values, so if we put by force, put Pete over here, Tom will be overwritten, right? So now we have to find some alternative way, and as we know that we have only 5 keys, and we used a modulo 5, that means we use the table with exactly 5 spaces, so definitely there is an empty space for Pete. Now our goal will be to find that empty space. Okay, so that somehow we will get this position and up this position. If we find this position for Tom, for Pete, then it's okay, right? So the challenge part over here, that sometime it will arise, that sometime there will be some duplicate hash index values. Okay, and then we need to use an appropriate hash table, hash function, sometime one function, sometime two functions, sometime combination of two functions. Okay, and so that this overwritten can be avoided, and all are placed in appropriate position. Okay, this is the goal of hash functions. Okay, so far, does anyone has any question? Everybody is okay? Okay, that's good. So now let us go. We will see that there is a way how to find the position here, this position with index 1 for Pete. What will happen actually, whenever Pete wanted to stay here in this position, it will say that, hey, this position is occupied, go next, look for the next position. The next position is also occupied by Harry, then say, go next, go to next position. So this position is also occupied, so then it will circular, like a circular, to go to the top, and this position is also occupied, so then it will see the next position, and next position is good, and this position is empty, so Pete will put there. So in that process is simple. What is doing, it is getting another index and then linearly increasing one by one. That is, it is checking, the first place, first occurrences. If it is not available, then it is going to up, then going up, going down, and then going by ODC. Or it can be happen that it could search for the previous position. Okay, so it can be happening both way. So this way is called linear hashing. Okay, it will be searching for available position, okay, linearly in a sequential order, maybe forward or backward. Usually we do forward, but you can do backward. Or it can be double hashing using two hash functions together, or it can be a quadratic hashing using a quadratic function. Okay. So the goal of this function is to reduce or resolve collisions.
I think there's a typo. It says kids. I think it's supposed to say kinds. In the first yellow text.
Finding the next empty cell.
The first red dot.
Okay, there are three kinds of methods to find the next vacant cell in the array: linear hashing, double hashing, quadratic hashing.
Yeah, it says kids, not kinds.
Use the same.
Oh, okay. Even thank you. Even I skipped it. Kinds. It should be kinds. Okay. There's a typo. Okay. Nice. Sometimes we go through, but we don't understand. We don't realize. Okay. So the goal is what is the goal of using hash functions to resolve collisions, right? And what is a collision? Yes.
When two authors try to take the same ID, so like, if it's like two try to use a 5 ID, then they pack one, right?
Yeah, if there is an index that is already being used, right? Already used, so then. Okay, these are self-explanatory, as I said. Okay. So the hash function is, as I said, that hash collision detection and then collision resolving purpose hash function is used. Okay. So for instance, there is a universal set U over here, and then the universal set for keys. Okay. So then it holds the keys K1, K2, K3, K4, and for instance, and hash functions is applied with these key values, right? As I said, the keys can be any data type. It can be numeric data type. It's easy if it's numeric. Okay. But it can be a string, as I saw that a few minutes ago. We convert a string to integer using ASCII value, or any other ways you can use. Instead of ASCII value, if you can use the position, for instance, if say A equal to 0, B equal to 1, C, D, E, F, G this way, or A equal to 1, B equal to 2, C equal to 3, and this way, whatever process you apply, but you have to apply same process, right? So then this is the hash function. You will get some appropriate index value, right? This is the table. This table, it calls as index, and it contains the value of keys, right? So the hash table contains two things. Okay, it contains index and associated keys. Okay, not values. Okay, so so then how do we resolve collisions? The process is going to the next searching. In some books it says by searching, or it's called chaining. Why it is called chaining? The concept is that what is that? It increases its small index. It uses another index, and then it increases that index by 1 from 1 to m minus 1. So I'm coming just that way. For instance, let me give you an example here. Okay. For instance, if I have my universal table what you say set of these keys K1, K2, K3, K4, to maybe it's just K6, whatever values you have, and then using a hash function, it's more likely that you will get some index, same index for 2 or more keys, right? For instance, for keys 5, 7 and 2, we got same index. In that case, there are ways, multiple ways. One of the solution is that using a chain. What is a chain data structure? Linked list, right? So here use another linked list, a small linked list. Okay, so whenever a value appears, okay, if the value gets another duplicate, so whenever an index value okay appears, if it is blank, then put over there. If there is another same index, then make a linked list, maybe singly or doubly linked list over here, and then there will be chain, so the next value will go there and the next value will go there. So for instance, by looking this small linked list, we know that for keys 5, 2 and 7, key 5, key 2 and key 7, we have same index. Okay, so for instance, now our hash function will know that it exists, k2 exists here in this position. Okay, and if it is not the first value, then it will go to the chain and linked list. It will look for the next value and look for the next value until it gets. Okay, and this is the way how we can resolve collision. Okay, but there are alternative ways. Another alternative way is that, for instance, k5 is already occupied in this position. Now for k2, whenever it is for k2, then look for the next or another empty cell, empty position, and there, for instance, here, and then k2 will take that position, and k5 will know where is the next one. There will be link between k5 and k2. Okay, and for instance, this was k7, maybe k7 will go over here, but there they will know that this k5, k2 and k7, they have same index value. Okay, but whenever there is a way, we call this probe, we count probe. That means how many hops we need to, how many steps we need to go. Okay, that is another way. We will see this, maybe not today's lecture, in next lecture we will see this. Okay, but this is the simplest way. For instance, this is, for instance, 49 and 86 and 52, that all of these have index I. Whatever I is, I may be 2, 3, 4, 1, 5, 6, 7, whatever I, that doesn't matter, but they are same. Okay, but they are over here, they generate same index, and then here they are linked using a linked list. Okay, and here the access time, okay, will be still pretty constant, because it will come over here in constant time. Then it needs to three more linear search, right, in a linked list. But in the very worst case, if all numbers happen in same, all numbers generate same index. In rare case, for instance, if all numbers generate same index, so then all will be in one chain, right? If you have 10, 30, whatever numbers are, all will be in chain. In that case, the access time will be theta. It's the very worst case. But we do not expect that that will happen, right? For all will be in same all will generate same index. But so far, do you recall that we already used hash function in one of our previous algorithms? Do you remember that what algorithm we use hashing? We did not use, maybe you wrote the one line of code that use hash. It is close to searching, one of the searching algorithms. Linear time searching algorithms. Remember? How many linear time searching algorithms we studied? Counting, right? Now what is next? Redis. Then what is next? So in bucket sort, we use hash, right? Hashing, right? You remember that there is this one line that says use hash method. And using hash method, they put them different number in bucket, different buckets. Maybe the hash method was there, for instance, whatever we use for numbers, modulus 10, right? Getting a number, the numbers are keys, and whenever you take the modulus 10, and you are getting the remainder, right? Maybe 5, 2, 3, 6, 7, and you are putting those numbers in a based on the buckets. That was where we already use indexes, so like hashing, okay. And hashing also used in encryption, data encryption. If you know about encryption, for security and privacy purposes, data are encrypted, changed, like for instance password, okay. Whenever you password internal, almost all system, they change the password in different numbers, so that from the other side, in the customer service person, even they have the database, they cannot see they don't understand your password. Okay. So the chaining is like, for instance, here, okay, for n keys with m slots. So what is the m over here? M is the number, for instance, we are using for modulus. Maybe modulus, we saw modulus 5, modulus 10, with whatever the number, okay. And we use another load factor, this is called alpha or I, whatever you say. Then alpha is sometime it can be 1, it can sometime n divided by m. If n equal to 10, then m equal to 10, then alpha will be 1. So that means you are linearly searching, checking for the next availability, next. Sometime if you may, for instance, if n equal to 10, and then there are 10 entries, and then if you use m equal to 5, then 10 divided by 5 equal to 2, right? So it will jump every other spaces, okay. So what value of m and alpha, you will take that difference on the data and your wish. There is no hard-coded rule for this, but we will see that some examples here, okay. So in the chaining case, if it is unsuccessful, for instance in the first phase, if it does not find an empty position, then it needs to look for the next available position, right? So in that case, you need some extra time. So it says theta 1 plus alpha. So still it is pretty constant, right? A little bit more time, but not big. Is better than theta n. Okay. Sometime you may find for alpha equal to 1, or you may go alpha equal to 2, 3, 4. But one thing, that alpha will be always less than m. So it is limited number. Okay. Now let us see some examples. So how do we choose hash function? As we said that our goal will be to choose a good hash function. And what is the property of a good hash function? A good hash function should distribute the keys uniformly into the slot of the table. Which table? our hash table. Okay, and our goal will be choose a hash function that uniformly distribute, but sometimes it may not happen. This is why sometimes we may need to use a different or two or more or different kind of hash functions. Okay, so the simple one is hash function, is the simplest one is division method. It's called, how do we find the hash function? Is k mod m. M is any numeric value, positive value. Okay, m, usually you can see that m is the number of total keys. Okay, m is the number of total keys, or sometimes it may be double. That difference one, but at least we saw that if m is number of total keys, then it is good enough to start. And k is the actual keys. So if the k values are integer, then it's fine, right? So m will be integer number and integer number mod integer, then we will get a value. But how about if this k values are not integer number? Then we saw that the few minutes ago an example that we can convert it by forcefully to integer number, right? Even a string we can convert an integer using ASCII values or using your own method. Because whatever approach you use, that should be standard and that should be applied for all keys. Okay, that is good. So for even we saw that for a string, okay, if we take ASCII code and then a polynomial equation, then we got some values, and taking m, we are getting some other kind of values. That is called we get index, right? And based on the index, we put these keys on the index, associated index position. Okay, so we map a key into one of the m slots by taking the remainder of k divided by m. That is the modulus operator that says. So here the condition will be all keys are either integer or it can be converted to integer. Okay. So if they are not integer, and they cannot be converted to integer, then there are other ways. For instance, if they are string and you don't want to convert them to integer, then there are a way. For instance, you can use if-else statements to find out what is the first character. If it is O, then it goes one bucket. If it is B, then it goes one bucket. If it is D, then it goes one bucket. Another. You can do it in multiple ways, okay? But for simple, this is the simple one, the division method. It takes for k either integer or can be converted to integer. K mod m, okay? So if we say k mod m, then what will be our hash table size? M, right? Its index will be 0 and last index will be m minus 1. That's 0 to m minus 1 equal to m, right? For instance, like this. If you have keys 36, 18, 72, 43 and 6. Okay? These are original keys. And the left side, what you are getting, hash keys. Sometimes some books says hashed, S-H-E-D. Okay, passive hashed keys, or you say this. So here they are taking with modulus 8. I don't know why they are taking modulus 8. How many numbers? 1, 2, 3, 4, 5. So as I said that anything you can do. You could take here modulus 10, m equal to 10. You could take m equal to 5. At least you need to make 5, right? There are 5 numbers. So m needs to be at least 5. But it can be 10. So they put just 8. Okay. So it doesn't matter. So here they use this hash function. If m equal to 2 to the power p should be 2p to the power p or just p, then the hash does not even depends on okay, it's 2 to the power p. Okay, so in that case, for instance, if they take modulo 8, then they are getting hash value 4, right? So then on the in the index table, on the this is the actually hash table with index 4. This is the 4 index. Which value will appear? 36, right? So whatever we find that this index value 4 is associated with this 36, right? Now there is an internal relation. Okay, there is a connection between this 4 and 36 because this 4 is generated from 36, right? And this that you should see this way. There is no collision, but they appear nicely. And sometimes if you say, hey, I have only 5 values, keys, why I'm going to use a table with index or 8 indices? So in that case, you can use modulo 5, and that maybe there will be some collisions, and then you need to resolve that collision. So collision may arise or it does not arise based on your hash function you're using. For this one, is hash function is that k mod m. Okay, and m is your choice, and k will be each of these values. Okay, for the first time k will be 36, next time k will be. So we can run a loop, right, to pass each of these keys, each of these values to this hash function. Okay. So the best way, you will see that later, that to find a k, to pick a k is a prime number. Okay, is a prime number. Pick a k is a prime number. Is the best for the best case that some studies and research found, and the book will see the prime number. If k is a prime number, that will hopefully will develop a good hash function. Okay, but it's not required to be prime number, but usually you can put prime number. Prime numbers means 5, 7. Okay, but for instance, we see that for prime numbers, if your key is 10, 20, 30, then the modulus will be 3, 6, 3. But for prime numbers, if we say non-prime numbers like 10, m equal to 10, for all cases 10, 20, 30, they will generate same index. So for multiple indices with same value, you will need another chain with linked list that will be maybe larger. So this, instead of using m equal to 10, if you use m equal to 7, it will do better. But that doesn't guarantee that will happen. So there are two kinds of hash functions. One is called open addressing, another is called closed addressing. Let us see that open addressing. Actually, we will discuss this in our next lecture. Okay. Just let me go a few things, and then we will skip it. Next lecture is available. Is sufficient for us. So in an open addressing, our focus is to create hash function in the form h of k and I. We are taking another argument I. Okay, we know the k value, right? And I, so previously we discussed alpha. We have alpha, right? So alpha, that means alpha or I, it can be same thing. Okay, so so now we have two parameters, one for k is k0, one for k, another for I. So what will happen if just first time we will put k I equal to 0 and then we will put k value. Okay, and for the second one, okay, and if that find this is good enough, then I'm fine. If that finds an empty space, but if that does not find an empty space, what we will do? We will keep k same, but we will increase I. Okay, maybe if we increase I from 0 to 1, we will find a empty position, empty space. Okay, even if we do not find for 1, we will increase I by next I by 2. So then we will check for same keys. For same keys, we will look for empty space. For instance, here, and then up to what do we need to do? We need to go maximum m minus 1, and definitely we will get an empty space if our hash function is appropriate. For instance, here we discuss here. So here m equal to 5, right? So for instance, if it, for instance, for Pete, we did not find an empty space, right? So initially I equal to 0. Then we increased I by 1. Okay, so then it goes this position, then it goes this position. Okay, and then we increase I, then it is a circular array, then it goes this position, and then it got after 4, if you say this one is 2, right? Then 2, then 1, 1, 2, 3, and 4. For I equal to 4, it found its appropriate position. So we are not changing the keys, we are changing, these are called steps. Okay, and in in terminology it called probes. How many probes you are, maybe that how many attempts you need to find an empty position. So here that is for I value. Okay, so I value is, it denotes the number of attempts. If it is successful in at first attempt, then I value is 0. If it is not successful in the first attempt, it is successful in second attempt, then I value will be 1. So these are called probe values. Okay, and the maximum we need to go m minus 1, and hopefully we will find, definitely we will find an empty space at this position. Okay. So this is called linear probing. So linear probing, that I is probing, so that we increase I 1 by 1, 1 by 1, linear probing. See, this is the hash function. For instance, if it does not work, okay, so that we sometimes we use another hash function. This is k is a hash function, that is a combination of another k is another hash function, and that this I is the attempts, is called probe values over here, and so this is combined actually. There is a mistake over here. There will be one more parenthesis here. There will be one more parenthesis here. Is there a parenthesis? There is no parenthesis. Okay, so HK. Oh, it is already, okay, sorry, it is already, it has this parenthesis. This parenthesis is this. Okay, so this is called linearly probing. It's a linear probing. There are other things that is called quadratic probing. It is using this is I to the power 0, I to the power 1, I to the power 2. It's quadratic method. Okay, this kind of, like for instance, I values are generating indifferently. Okay, and then there are other methods, for instance double hashing. For instance, this is H1k and this is H2k, and H_k is that combination of H1k plus I into H2k. It can be different. You can say you can multiply I with H1. That doesn't matter. But ultimately what is happening here, this is using two hash functions. Okay, or you may say I equal to 1 constant, right? So that even here H_k equal to H1k plus H2k, but that may not resolve with probes. This is I which needed to be rotated from 0 to k m minus 1. Okay, and if the first or default, or say I equal to 0 value does not become successful, then I will the next value of I will be used. And this way, for instance, this way, so we saw linear hashing, just a linear. This one is linear probing. Okay, what is the probing over here depends on I value. Okay, how I value will be increased. It can be linear probing. I is linear function. It can be quadratic. I is here. The first term it has I to the power 0, right? 1 means I to the power 0 over here. So it has I to the power here. It has I to the power 0. Anything to the power 0 equal to 1. So this is why they did not write 1. So this is the H-k plus C1i, C2i, and here C1 and C2 any constant. You can put any constant, and for same constant, same will be used for all keys. Okay, so this is called quadratic probing. Why is quadratic? So I has power 2. Okay, quadratic probing, and we saw that there is another kind of probing. This is called double hashing. So here double hash function, right? So these names implied. Okay, these are the process. Maybe we will discuss this in our next lecture, and when we discuss this, then we will see in our next lecture. Actually, we will practice this, and once you understand this, you will get some similar test questions, not exactly same, and similar quiz questions or assignments. Okay, then I will give me 2 more minutes, please. I will update assignments and quizzes for. Okay, and what I want to do, I want to keep them before your test, before test 2. Okay, so that you practice this, and then so hopefully this was a weekend. These were due in this weekend. I will make 2-3 days in the middle of the next week, so that before the test you complete the quiz 4 and assignment 4. Okay, maybe Monday or Tuesday night I will make this. Okay, and then another thing is that there is another announcement. So everybody please be ready for the test. Okay. Now please give me 2 more minutes. Let me get my attendance. Okay, does anyone has any questions so far? These are something interesting, right? You can study yourself. There are tons of this. Even if you read the book, you will find this. You will get on this. There are many, even the audios, videos, podcast. Even when you drive it, you can listen. Then you can understand. These are not complicated that much. Okay. Okay. Thank you everybody for tonight. But give me